Hello again. This video is part of a tutorial containing 3 sections. Now we move over to the second section on the solving with OpenGeoSys.
For the installation, we refer to the OpenGeoSys website, a docs and user guide. You find the installation of the binaries, which is quite simple, but we also would like to show you the installation from the source code. This is under developer guide, and there you find how to get the source code. This is the ideal installation. We could give another tutorial just about the version control and the compilation, and to give you the idea how it works, we show you the link to the repository. This is Git, and there you find the link you need. We run git clone with the copied link. Since we already did this, we enter this as a comment. If you do it, you should remove the hash key in front. After cloning, the source code is on our disk. You can take a look and find the C++ source files, documentation, some test cases. It is common to create a directory for the release, possibly another one for the debug. In this, we run cmake to set all the make options. Cmake with reference to the source code. We cannot speak about all of the options. We show you the most important ones. We are going to use only small deformation, the small deformation process. So we disable any other process to cut down compilation time. We build the utilities like check mesh we just used, and we won't need all of the elements. We won't need cuboid, prism, pyramid. We just use simplex element, triangles or simplex element in 2 dimensions. We check for Python because we use Python, for example, for the boundary conditions, and we won't change anything else. We run configure. It goes well. We generate the make files and run make with the power of 8 cores. Build finished. We find the binaries in the subfolder bin. There's the mentioned check mesh beside many other command line utilities, and there's the main executable, OGS. We check just by running OGS with the help options to get to know the command line usage.
As the meshing process is over and we have our boundary domains and also our bulk finite element mesh with the different material domains, it is time to create our project description. For this, we also will have to specify time-dependent boundary conditions using a Python script. All of this will melt into an input file, which then will be processed by OpenGeoSys. But how to arrive at such an input file? On the official OpenGeoSys website, in the benchmarks section, you find many of those examples that you can use for getting started. In our case, it could be, for example, a small deformation tutorial, and here we can directly download the project file. Now you see the OpenGeoSys project input file for our teaching example. It is an XML file containing the definition of several important things: the meshes, the Python scripts, the processes, the time loop, the parameters, the process variables, and the nonlinear and linear solver settings. Let's start with the meshes. Here we define the bulk finite element mesh and also the meshes for the different boundaries. Then we specify the name of the Python script for our a bit more complex time-dependent boundary conditions. Then there is a section on the process. In our case, it is a small deformation process where we use integration order 2 and assume linear, elastic and isotropic material behavior for all our different material domains, which we can distinguish by the material ID that we had prescribed using Gmesh. Furthermore, we need to specify the material parameters, which is done further down. Then we have a specific body force due to the gravity, and we define the output quantities derived from the primary variables, namely the stresses and the strains. Now we go into the time loop, where we have some settings for the nonlinear solver. Especially important is the convergence criterion and also the time stepping. We end our simulation after 1 second. Could equally be 10,000 years, which would be more realistic for an advancing glacier. But as we are dealing with a purely elastic problem, the time scale is irrelevant. Then we define the number of time steps and their size, and in a very similar way, the number of outputs. Now there is a section on all the parameters. First, we define the material parameters with respect to the different material IDs, and we have a group for Young's modulus, where you can see that the first sediment layer is rather soft, whereas the second layer is a bit stiffer. The third layer is soft again, and the underlying rock bed behaves very stiff. Likewise, we define Poisson's ratio, and at the end we have to define the density, where the value is irrelevant for the simulation results, and we specify the initial and boundary values. Here we have 0 initial displacements. After this, there's the section on the process variables with the definition of the boundary conditions. As you can see, we apply Dirichlet type boundary conditions on the left and right boundary and at the bottom boundary, where we have either 0 horizontal or 0 vertical displacement. On the top, that means on the surface, there's a special boundary condition for the glacier advance. At the end of our project input file, you can find some more settings for the nonlinear and linear solvers. In our OpenGeoSys project input file, we call a Python script for the definition of the time-dependent boundary conditions. And now we are going to have a look at this file. At the beginning, we import OpenGeoSys and a glacier class. Then we specify some geometrical input parameters, for example, the length of the domain and also the maximum length and height of the glacier. In the class for the boundary conditions in y direction, we have a constructor where we instantiate a glacier object, which then in the getFlux member function is used to return the normal stresses as a consequence of the weight of the glacier. The flux boundary condition here means the flux of the linear momentum. In other words, the components of the stress vector at the surface. Let's have a short look at this glacier class. Basically, we calculate the normal stresses from the weight of the glacier, incorporating the density, the gravity, and the local height of the glacier, where both height and length of the glacier evolve with respect to time. And here we have a linear evolution mimicking the advance of the glacier. Back in our Python file for the boundary conditions, we have to create an object for the boundary conditions in y direction, and this object will be used in our project input file. Back in our OpenGeoSys project input file, this is the place where the Python boundary condition object for the glacier is then called. Now everything is ready to start our simulation. For this we use the binary for OpenGeoSys that we had created before. And for the log level flag we use the debug setting such that we have some more information and output during the simulation. Starting the simulation, at first the glacier class plots the evolution of the glacier, and this way we can convince ourselves that this evolution is the way we wanted it to be. Then the simulation starts, and at the end of the simulation we see that OpenGeoSys has terminated successfully. Now we have a look at all the output data that just has been written, and we see many unstructured grid files, and they are all embraced in this ParaView data file that we can now evaluate using ParaView with this command.